Hello, welcome back. So in your last lessons, you guys learned about intermediate value theorem, and you learned about more about limits. In this lesson, we're going to take a look at relations and inverses, some of which will be familiar, hopefully. So the objective of this lesson is that we will be able to find inverses. Maybe you know how to do that, right? And maybe you remember some of the fun facts that we learned about inverses, as well as state some important properties. Like if you're looking at a function, how do you know if the inverse of that is going to be a function? How do we determine the domain and the range? What about any restrictions that might need to come in or happen? So that is what we're going to be looking at through this lesson. So let's get our notes ready and get started. So inverse relation. The ordered pair AB is in a relation if and only if the ordered pair BA is in the inverse relation. That was fun fact number one, right? So you can switch the variables. If we're looking at a graph or a relation, how do we determine if that itself is a function? Maybe you remember the vertical line test. So extending on that, if you're looking at a relation, how do you know if the inverse of that relation is going to be a function? Right, so using this idea, or extending upon that, the horizontal line test. Which relations below, so these four, are functions? Which relations have inverses that are functions? This one's going to be a function, not a function, not a function, a function, right? So here we're looking at the vertical line test. Here we're looking at the horizontal line test. So here we just did the vertical line test. Here we're going to do the horizontal line test, right? So horizontal line test, yeah, its inverse is going to be a function. Check. What about this one? Oh, its inverse is going to be a function. Oh, inverse is not going to be a function. Finally, no, not a function. Right, so switching the variables, horizontal line test. If f is a one-to-one function with domain D and range R, then the inverse function of f, denoted f inverse, right, that's inverse notation, is the function with domain R and range D, defined by f inverse of b equals a if and only if f of a equals b. So I want to go back right here. What is one-to-one? One-to-one is saying that every input has one output, but also every output has one input, right? So it is a one-to-one function if the given function and its inverse are both functions, right? So not every function that you deal with is going to have an inverse that is also a function. For instance, a common one that we look at, or you guys have worked with, is a quadratic, right? A quadratic is not one-to-one. Maybe you remember doing some domain restrictions last year, so that we could restrict our quadratic and give it a restricted domain, limit its domain, so that we're forcing it to have an inverse that is also a function, right? But in its sense right here, it would be plus or minus the square root of x, which is not a function, right? That's a parabola that opens sideways, not a function. Fun fact number 3. So I kind of just said this. Not all functions have inverses that are functions. From this definition, what is required for f to have an inverse? It has to be one-to-one. If it is not one-to-one, its inverse is not a function, right? So every x has one y, every y has one x. So if we look at this example right here, our goal is to find f inverse of t, and we're given f of t equals t over t plus 1. And we want to after we find the inverse, we want to state the domain and the range of its inverse. So we're going to start by finding the domain and range of the original. I'm going to do it up here so I don't run out of room. Domain. Well, I can't divide by 0. So the domain is going to be everything but -1, right? I'll go with negative infinity to -1 because that will make this 0. Not including it, -1 to infinity. I could have written that different. But that's how I chose to write it. The range, well, is there anything that we need to kick out of the range? Isn't there a horizontal asymptote? How do we figure out where that is? We can figure out where that is by looking at the leading coefficients, because they have the same degree, right? So it's not, remember, top heavy, bottom heavy. These are the same. They both have a power of 1. They're the same degree. So it's going to be the ratio of the leading coefficient. So I'm going to end up with a horizontal asymptote at y equals 1, right? It's 1 over 1. So your range would be from negative infinity to 1 and 1 to infinity. It's going to skip over 1, right? Or all real numbers except for 1. All real numbers except for -1, if you want to write it like that. Okay, great. So we've done step 1. Let's keep going. Now we want to switch the x and the y, and we want to solve. So we're going to actually solve for the inverse. So we're going to undo order of operations, go backwards. So let's see. I'm going to use x and y. I'm going to say x equals y over y plus 1. And I'm going to solve, my goal is to solve for y. So I'm going to start by multiplying both sides by y plus 1. And I'm going to distribute that x. So xy plus x equals y. I'm going to go ahead and subtract the y and subtract the x. And then I'll factor out a y. So that's going to leave me with x minus 1. Oh no, I'm getting really small in this corner. Sorry, guys. Negative x over x minus 1. So the inverse that I have, f inverse of t equals, so I'll use function notation there, negative t over t minus 1. Okay, step 2, done. Replace y with f of x, making sure you use inverse, making sure your inverse is a function. We're good, right? This is a function. I already did that. Switch the original domain and range for inverse, making sure there's no new issues. Okay, so now I'm going to have f, I'm going to rewrite it. F inverse of t equals negative t over t minus 1. So let's see, my domain should be all real numbers, but x cannot equal to -1. I'm sorry, x cannot equal to +1, right? I'm switching them. My range should be all real numbers, but x does not equal to -1. Let's see, is that true? My domain, yeah. Oh, I guess t, darn. Sorry. My domain, yeah, this can't be a 1. Everything else is fine. And ratio of your leading coefficient, because it's not top heavy or bottom heavy, it's the same degree. The ratio is -1. So that's what's kicked out of my range. Yeah, so that works, right? There was no new issues that came up. Amazing. Ooh, the inverse reflection principle. A relation and its inverse are reflections of each other over the line y equals x. Remember this, right? It's reflected. If you take the x and the y value and you switch them, you end up with this nice reflection over the line y equals x. That was something you even did in geometry. That was another fun fact. Let's see. Can you guys find this inverse? Maybe pause the video and try it. And then unpause it and come back to check your work. Let's see, switch x and y. Ready now? X equals the cube root of 91 minus y to the third. All right, there was no domain restrictions here. It's a cube root function, so if I wanted to find the domain and range to begin with, it was just all real numbers. Okay, so I'm going to cube both sides. X cubed equals 91 minus y cubed. I'm going to add y cubed and subtract x cubed, and then take the cube root. So I get y equals the cube root of 91 minus x. Wait a minute. That was what we started with. Let's look. Look at that graph. It's a reflection of itself. So when you reflect it, you get the same thing. How fun is that? Let's see, do you remember anything? Am I missing anything about inverses? The composition rule, right? Fun fact number 5. This was the last one that we did last year. A function f is one-to-one with inverse function g if and only if f of g of x equals x, right? So it's like when you do something and then you do the opposite, they cancel each other out. And g of f of x equals x as well. If that's not true or one of them's not true, they're not inverses. That was fun fact number 5, right? So like this, if you staple it and then you take the staple out, you get what you started with. That's what we want if they're inverses. So let's finish up with an example of this. Use the inverse composition rule to verify f and g are inverse functions. So f of g of x, the square root of x squared plus 4x plus 1 plus 3 minus 2 equals the square root of x squared plus 4x plus 4 minus 2. I think we can factor this, can't we? This is, oh look, x plus 2 squared minus 2. Well, this is just x plus 2 times x plus 2, and then when you take the square root, it's just x plus 2 minus 2 equals x. Let's do it the other way too. G of f of x. Right, so the square root of x plus 3 minus 2 squared plus 4 times the square root of x plus 3 minus 2, sorry, plus 1. Oh, I should have left myself more room. If I go ahead and I square this, that doesn't seem very fun, does it? First, we're going to end up with x plus 3 minus 4 times the square root of x plus 3 plus 4. And then plus, distribute that. Oh, that's nice. Minus 8 plus 1. Okay, so let's see what happens here. These will go away. That's an 8. So I've got x plus 3 plus 4 minus 8 plus 1, unless I mathematically made a mistake somewhere, which is super possible. I don't think I did. Nope, I didn't. X is what you're going to get here, right? This is 7 minus 8 is negative 1 plus 1, so like these will all cancel each other out. You get x, right? So that verifies it. And notice the domain here. Right, for x is greater than or equal to negative 2. So we had to restrict it. So this is only looking at the right side of this parabola. Sorry, I'm gonna finish up with this while I'm here. This has that restricted domain, because if you think about this, it's a parabola, right? It's quadratic, and I don't want the entire quadratic, because we know that its inverse is not a function, right? We know that if we graph this and this, it's not gonna be a full reflection of it. So this is coming from the x-coordinate of the vertex, and maybe you remember this, right? To find the x-coordinate of the vertex from last year, hopefully. So if I do that, the opposite of b over 2a is where we're getting that -2. So that's just going to give you the right side of this parabola, which is, that makes sense because it's just the top when you're graphing it. So those would be inverses of each other. Amazing. All right, everyone. So hopefully this was a good review of some of the things that we learned about relations and inverses to refresh your memory and expand on it a bit for this year. Thanks, everyone.